In Chapter 12, we're going to look at chemical bonding, and we're going to start to look at how atoms come together to form molecules, what shape those molecules have, and be able to give a lot more description of what's happening within the molecule so that we have a better understanding as we get into gases, solids, and liquids of why various chemical properties are occurring. To understand this, we're going to look at the electrons because the electrons are on the outside of the atom and they're going to be the ones involved in the interaction between most atoms. So we're going to go through in this chapter a number of different things. We're going to start with types of bonds in this first video, and then we'll get into ionic bonding, covalent bonding, we'll draw Lewis dot structures, we'll get into the shapes of the molecules and the polarity of the molecules. When talking about chemical bonding is the term that we have for the force of attraction between atoms or ions due to the behavior of the electrons. Ions are attracted by the positive and negative charges of the ion. Those positive and negative charges occur when electrons are transferred between one atom and another. In our covalently bonded atoms, we're going to have the electrons being shared, and we're going to form the different types of bonds. But it's this interaction of these valence electrons, those electrons on the outside of the atom, that determine the type of bond that's being created and give us the structure of the molecule. You could also describe it as a force that holds two or more atoms together and makes them function as a unit. Now, when we talk about bonding, there are many different types of bonds, and we're going to start off here with the various different types of bonds and explain what those types of bonds are and how we can identify the type of bond that's occurring in most molecules. First type of bond we look at is known as an ionic bond. An ionic bond results from the electrostatic attraction of an anion, a negatively charged ion, and a cation, a positively charged ion. Generally, we're going to see ionic bonds in metals bonding to nonmetals, metals forming our cations, nonmetals forming our anions. Covalent bonds result from the sharing of electrons equally. For example, in the picture at the very bottom of the screen, we see two hydrogen atoms, the blue dots being the likely location of the electrons in the 1s orbital. They will come together, share those electrons, and you see they now form what looks like a place where we expect to find the electron that's around both nucleus. These are known as molecular orbitals. We're not going to go into a lot of detail in this course about molecular orbitals, but you can start to get the idea that these electrons are forming an orbital that goes around multiple nuclei instead of around the one nucleus. Generally, we see covalent bonds between two nonmetals that are bonding together. And the other case we could run into of bonding would be metal with metal, but we're not going to go into a lot of detail in this course on metallic bonding. Within covalent bonding, we do start to see something known as a polar covalent bond. This is sort of an intermediate case in between covalent and ionic. You'll sometimes hear covalent referred to as pure covalent or just covalent, and then we have this other case known as polar covalent. This is kind of in between ionic and covalent in the sense that there is a sharing of electrons like a covalent bond, but you also get partially a charge between the two atoms for that electrostatic attraction. Basically what's happening here is the electrons are being shared, but being shared unequally. So you see here an HF. Instead of having the electrons spend equal amount of time around fluorine and hydrogen, you get this kind of shape here, spending very little time around hydrogen and much more time around fluorine. And we get what's known as a partial negative charge, which is this symbol down here, Greek letter delta, lowercase, minus, and then a partial positive charge on the hydrogen, the delta plus. Now, the way to really understand what type of bond we're going to have is to look at another periodic property known as electronegativity. Electronegativity is the attraction that an atom has for the electrons on another atom. This is going to be very low for metals and very high for nonmetals. If you think about it, a metal generally has one or two, possibly three valence electrons. To be stable, you need a full set of valence electrons, which ends up being 8 valence electrons. So gaining another electron is not going to make the atom significantly more stable. Whereas for nonmetals that have close to the noble gases and have 6, 7 valence electrons, you see a very high electronegativity value because gaining 1 electron could make the atom electrically stable. There's a table in your book on page 403 that will show these values, and I also have a table in the next slide. Fluorine is the most electronegative element. It decreases as we go down and increases left to right. We do not include the noble gases in the chart of electronegativity because they are stable, so they're not going to be gaining electrons. They actually have 0 for electronegativity values. In most cases, there are the one case here of xenon, which does have an electronegativity value, is the one of the noble gases that occasionally does form compounds. So you see the values here with the lowest being francium, down here at 0.7, the highest being fluorine at 4.0, and you see that we increase as you go up and to the right. So the value is increasing as you go up and to the right. The lowest values are your alkali metals at the bottom of the table, alkaline earth metals, and your highest values are going to be generally your halogens and things on the very top of the table. Now, the one really interesting case that we do need to pay attention to is hydrogen. Hydrogen, you'll see, has a value of 2.1, which does not fit in the trend that we were looking at because it's actually way here to the left. Remember, hydrogen can go in one of two places. It could also easily go here above fluorine in the periodic table. For electronegativity, you need to understand that it actually fits in the trend in between boron and carbon. So it has a higher electronegativity value than boron, lower than carbon. So you need to know that hydrogen, in terms of electronegativity, fits between boron and carbon. Now, subtracting the electronegativity values will allow us to figure out what type of bond we are dealing with. Generally, the scale works. If the difference is less than 0.2, we have a nonpolar or just pure covalent bond. If it's between 0.2 and 2.0, you get a polar covalent bond. And anything greater than 2.0, you get an ionic bond. So the more ionic character, the further away they're going to be on the periodic table, the bigger the difference in electronegativity. And this tells us the probability that the electrons will be around one atom versus the other. So the higher electronegativity value atom will have the electrons around that atom more often than the lower electronegativity atom. Now, we're generally not going to use that numeric chart to figure out bonding in this course because you can just by the trend have a good idea of what's happening. So generally, when we think of bond types, covalent is going to be generally happening with only one elemental type. So these are your diatomic molecules. These are the cases where one of the same element is bonded to another of the same element, another atom. We refer to this as nonpolar covalent. The diatomics are a great example of this. But you can have in a larger molecule a pure covalent bond between carbon atoms, nitrogen atoms, anytime you have two of the same nonmetal bonded together. Polar covalent is going to generally happen when we have two different nonmetals. For example, hydrogen and oxygen. Oxygen is more electronegative than hydrogen, so the electrons will spend more time around the oxygen, making it partially negative, and less time around the hydrogen, making that partially positive. Then ionic will generally occur when we have a metal with a nonmetal. So you're looking at opposite sides of the table, a large difference in electronegativity, the electrons will be transferred. So you can see the three pictures here. This is our covalent case. Electrons shared equally, it makes an equally sized orbital. Here's our polar covalent. The electrons are still being shared, but they're spending more time around the right atom, making it partially negative, less time around the left atom, making it partially positive. In this case, the atom here on the right would be more electronegative, and the atom on the left would be less. And then this last case is where we have ionic. Here we have a more electronegative element taking the electron to form a larger orbital, and the less electronegative element losing the electron, so it becomes positive, this one becomes negative, and they're held together by that electrostatic attraction. So let's look at some examples and go through what type of bond we would have. So in this case, hydrogen and oxygen, we would have a polar covalent, two different nonmetals. Nitrogen and oxygen, once again, polar covalent. In this case, nitrogen, less electronegative than oxygen, so if you wanted to, you could draw the negative on the oxygen, positive on nitrogen, positive on hydrogen, negative on oxygen. Magnesium and chlorine, metal with nonmetals. This is going to be ionic. Chlorine will become a negative ion, magnesium will be positive. Aluminum and oxygen, once again, metal with nonmetal, so this is ionic. Calcium and fluorine, once again, metal with nonmetal, so it's ionic. Fluorine and fluorine, two of the same nonmetal, so this will be covalent. Carbon and nitrogen, two different nonmetals, polar covalent. Phosphorus and oxygen, once again, two different nonmetals, polar covalent. Carbon and hydrogen, two different nonmetals, polar covalent. Now, if we go back through to put the partial negative and partial positive on these, carbon's more electronegative than hydrogen. Remember, hydrogen falls between boron and carbon, so we'd make carbon delta minus, hydrogen delta plus. Phosphorus and oxygen, oxygen's more electronegative, so it gets the minus, phosphorus gets the plus. Nitrogen's more electronegative than carbon. And in these ionics, we'd have a negative and a positive for magnesium, a negative and positive for oxygen and aluminum, and a negative and positive for calcium. So this completes the first video on types of bonds. In our next video, we'll look at ionic bonding.